Environment types are multiple. We distinguish between sorry, we distinguish between fully observable and partially observable, deterministic and stochastic, episodic versus sequential, static versus dynamic, discrete versus continuous, and single agent versus multi-agent. We also discriminate between known and unknown environments. So fully observable versus partially observable environments. Basically, a fully observable environment is an environment in which an agent sensors give it access to all the states of the environment at each point in time. So a fully observable environment in the case of our vacuum cleaner robot that we saw previously with 2 rooms and the dirt in them would be that it has an access to where it is and the state of the dirt in the position where it is. Partially observable would be basically that the robot has access only to the dirt sensor or to the position sensor, but it doesn't have the both. And so basically it has the information of, or that it can be this case or the case where it can be that it doesn't have the access to all the information in all the rooms at the same time. So basically our universe, let's say, our world, let's say, micro world is made of 2 rooms and with the positions. So you need to have a position in the room and you have the state of the dirt in the rooms. So in case you lack one of these information, then we speak about partially observable. In case you lack all the information, you have whatsoever no information of the environment, all the states or none of the states that the world is in, then we speak about not observable or non-observable environment. Regarding deterministic environments, so deterministic versus stochastic environments. In the deterministic environment, the next state of the environment is completely determined by the current state and the action executed by the agent. Now, in the case that the next state is determined by the actions of the agent and some other agent in the system, then we speak about the environment that is strategic. Now, in case that we speak about stochastic environment, that's the situation in which the environment changes independently of the actions of the agent, but the change has some kind of probabilistic behavior, so you can apply some kind of distribution function for the change. In case that you cannot apply some distribution function, statistic distribution function, then we speak about non-deterministic environments. And then in episodic environments, we have an agent action that is divided into atomic episodes. These decisions do not depend on previous decisions or actions. So in episodic environment, an example is a robot on a conveyor belt that has to check the defects on certain parts. So whenever a new part arrives to the robot through the conveyor belt, the situation, the state of the part is not affected by the state of the previous part that passed through the conveyor belt. So here we have each episode which is independent of another episode, and therefore we call it an episodic environment, which is contrary to the sequential environment in which the actions in this period depend on the actions of the previous period. Like if you do some kind of planning of multi-robots moving through the space, needing to go from some origin destination to the target destination and picking up an object there, then all the processes of intermediate planning of the change of the states of the environment will be sequential. They will influence, one action in one state will influence another action in another state. In static environments, the environment is unchanged while an agent is deliberating. That means while an agent is deciding on which action to follow next. So an environment is semi-dynamic if the environment itself does not change with the passage of time, but the agent's performance score does. So this example is chess playing with the limited time for each action. In dynamic environments, the environment is changed as the agent deliberates. So assume that you are a taxi driver, as we had example before. So this is an example of dynamic environment. In discrete environments, there is a limited number of distinct, clearly defined percepts and actions. So an example of a discrete environment is a chessboard. We have exactly a limited number of different discrete states in which the environment can be. This number can be limited or unlimited. Okay, so in case of continuous environments, this is the actions and the states of the environment are continuous. An example can be a taxi driver. So taxi driver, each position of a taxi driver is not a discrete number. It cannot be represented by discrete numbers. The GPS positions and so on. So this is a continuous environment. Regarding the difference between single agent and multi-agent environment, well, this is quite simple. So in a simple single agent environment, you have just one agent. In multiple agent environment, you have multiple agents. But the question here is, if you are a designer of the environment, how are you going to model the system in example of a taxi driver, for example? So will you consider for a taxi driver that all the other vehicles are agents or they are just objects? So you can communicate with them or not. You can influence their actions. You can negotiate with them the ways of moving or the routes or not. In this table, we have different examples of task environments, such as crossword puzzle, chess with clock, poker, backgammon, taxi driving, medical diagnosis, image analysis, part picking, robot part picking, refinery controller, interaction with engineering tutor, and so on. So now, for each one of them, you are encouraged to read well the definitions. I will give you an example. So crossword puzzle is fully observable. It is deterministic, it is sequential, it is static, it is discrete, and it is a single agent environment. Chess with clock is fully observable, it is strategic, it is sequential, semi-dynamic, it is discrete, and it is multi-agent. Now think about a poker and backgammon. If you do not know what these games are, I encourage you to search on Google and Wikipedia. And here is the solution for the first part. For poker is partially observable, stochastic, environment is sequential, static, discrete, and multi-agent. And with backgammon, the environment is fully observable, stochastic, sequential, static, discrete, and multi-agent. Now we move to agent types. There are 5 basic types of agents in order of increasing generality. The first ones are table-driven agents, then simple reflex agents, then model-based reflex agents, goal-based agents, utility-based agents, and learning agents. The last one are most general ones. The most simple one is a table-driven agent. So how does the table-driven agent work? In the upper part of this slide, you see the basically algorithm, and underneath you see the architecture of the agent. So basically, for each percept, the table-driven agent program is invoked and returns an action each time. So basically, there is a table saying, for this percept, do this kind of action. Now the question here is, what do you think? How many lines of this table should we have for a very simple environment? Let's give an example of a chess. So in the case of chess, you would have basically 10 to the power of 150 entries for the lookup table for chess. So you can see here that this is really not computationally efficient. It is not memory efficient. This kind of agent would not work in the real world. Next, there is a simple reflex agent. So this kind of architecture that you can see here in the image, and also you can see the function describing this kind of architecture. It learns a policy that maps directly from states to actions. So it is the simplest kind of, let's say, agents, not considering the tables which we saw that are not applicable in the real world. This one is applicable in the real world. So basically, it selects actions on the basis of the current percept, ignoring the rest of the percept history. I will give an example of the vacuum agent that we saw previously, a vacuum cleaner robot. And in the former part, we saw how it could be, its agent function could be represented as a table. Here, basically, we can represent it as rules. So if dirt is found clean, if there is no dirt, move to another room, for example. These kind of architectures can be applied also in more complex architecture. Here we have different hierarchies of architecture. These architectures are usually composed of more complex levels, but also of the simplest reflex level, where it is all about the instinctive behavior. So, for example, imagine that you have a car you're a taxi driver and the car in front of you is braking. So the reflection to this should be brake, right? Because if not, you're going to get into the accident. So responding to the car in front is braking will be initiate braking. So these kind of rules, we call them condition action rules. And these rules can be represented: if car in front is braking, then initiate braking. Since simple reflex agents are too simple, since they have no memory and they fail if the environment is partially observable, we need some kind of a model of the state of the world within the agent, such that an agent can respond to partially observable environments. But the most effective way to handle partial observability is for the agent to keep track of the part of the world it can see now. So an agent should have some kind of internal state that depends on the percept history and thereby reflects at least some of the unobserved aspects of the current state. And this kind of an agent is a model-based agent. So the agent should have a model first regarding its actions, how its actions change the state, the environment, and how its internal actions, for example, in the case of a taxi driver, what does steering left, steering right do in respect to the direction of the car, and then also in respect to the environment independently of the actions of the agent. So it is going to have some kind of a state within the within its architecture, which is basically going to help it to understand how the world evolves. So it's going to have some kind of knowledge of how the world evolves, what its actions do, what the state is right now, and what the world is like now. So based on the condition action rules and the knowledge about what the world is like now, it is going to know what action it should take next. And then this is going to be performed in the actuators. Actuators are going to be running in the environment. This is going to have impact in the environment. In the next iterations, the sensors are going to read the changes in the environment, and they are going to react iteratively to the environment until the goal isn't reached. In the model so far, the agents didn't think about the future. So the actions were about here and now based on some conditions action rules, right? Now, in this architecture, which is called goal-based agent, we have the goals that are basically there to lead the agent towards the goals that we want to reach. So this is considering the future. Now, we can include the goal-based agent with reflex agents and with the model-based agents, and we can combine these architectures to have more complex and more sophisticated behavior of the agents. Now, for example, let's give concrete examples about the taxi driving. So in the case of taxi driving, the reflex agent, if you want to go from your origin to your destination, the reflex agent, you're going to have to write many condition action rules to reach that specific um, uh, destination from your specific origin. Anytime the origin destination change, you will have to rewrite these condition action rules. For the goal agents, you will just have to change the goal, and the system will automatically adapt to the to your new destination. So, in respect to the reflex agents, let's say that now we have the questions of um, the consideration of the future, and for the reflex agent, we would have to write many condition action rules for each one of these goals. So the model-based reflex agents basically gives the model of the world, and the goal-based agents basically gives the context to what is the goal of the agent. However, in the performance of the agent in reaching that goal, we can distinguish between just two states. The goal is reached and the goal is not reached. Now, to increase the performance evaluation, let's say, of the these kind of agents, we use utility-based agents. So we use the concept of utility. So instead of having just two states, goal reached and goal not reached, we can also say how well did we do in reaching the goal. So the utility here is basically the internalization of the performance measure that the designer of the system proposed in integrating this multi-agent system, or the agent system, sorry. So if the internal utility function and the external performance measure are aligned one with another, then an agent will choose actions that maximize its utility and will be rational by the definition of the rational agent, according to the external performance measure. So it depends of how well the utility function represents the performance measure. If we work in the partial observability and stochastic environments, then basically we are not going to maximize the utility as we did in the deterministic environments, but we are going to maximize the expected utility of the action outcomes. That is the utility the agent expects to derive on average, given the probabilities and utilities of each action. Next one is the learning agent that can be divided into four conceptual components: the critic, learning element, performance element, and the problem generator. The most important difference between the learning element and the performance element is the learning element is responsible for making improvements in the behaviors and in the actions, and the performance element is responsible for selecting external actions. We have already seen before the performance element. So it is basically the entire agent architecture from before. So in the previous architectures. So it takes in the percepts and decides on actions, the performance element. Then the learning element uses feedback that comes from the critic on how the agent is doing and determines how the performance element should be modified to do better the actions in the future. The critic tells the learning element how well the agent is doing, and for example, in a chess program, we have for example, a percept indicating that the agent has checkmated its opponent. But if without the performance standard, we do not know whether this is good or bad. So we need a performance standard to distinguish between the quality of our actions. The last component of the learning agent is the problem generator, which is responsible for suggesting actions that will lead to new and informative experiences. So, for example, if the performance element had its way, so if we just use the performance element, we would keep doing all the actions from before and the system would not learn. It will be always same old, same old. So if the agent is willing to explore and have some combination between exploring and using the learned informations and the knowledge it has learned, it might discover much better actions for the long run. So the problem generator's job is to suggest the exploratory actions. Now, let's have an example of the automated taxi example, taxi driver. So basically, the performance element consists of whatever collection of knowledge and procedures the taxi has for selecting its driving actions. The critic observes the world and basically passes information along the learning element. If, for example, that the driver has turned left very abruptly, and the critic has observed that there were people very angry about that, it might learn that this kind of behavior is not adaptive. So from this experience, the learning element is able to formulate a rule saying that this was a bad action. Then the problem generator will identify certain areas of behavior that must be improved, and it will suggest experiments, and the learning element will make changes to any of the knowledge components shown in the agent diagrams seen in here.